Okay, let's take care of this. So the oxidation numbers, what do we got for the first one?
H plus.
We okay with this just being a H plus? How do you know it's an H plus? Just saying hydrogen's not good enough. Hydrogen with a non-metal, so automatically has to be +1. So since that's a +1, then we don't even need to look at the chloride version because it would have to be -1 to cancel out. And then the name?
Hydrogen chloride. It's an acid.
Starts with an H, right?
Yeah, that was my bad.
Why is it moving like that? That's annoying. Right, second one, cation. Anything else with that?
Well, you have to figure out what its charge is because it's in the middle.
How do you know it's +2?
You start with sulfur.
Because the sulfur's a -2 because it's in the oxygen column, and in an ionic compound, it just uses the normal -2 charge. And it's trying to be -2 because it's 2 away from the noble gas, so it'll accept those 2 electrons. And so then the name for this?
Cobalt 2. Cobalt 2 sulfide.
This is really hard. Wow.
Interesting.
This is really hard. Whatever. They must be trying to orient inside of the cell. I'm gonna have to get rid of the table version of this. All right, charges here.
Hydrogen plus.
Are we okay with those? The oxygens are going to make 8 negative total. The hydrogens cancel out 2 of that, then the sulfurs need to cancel out the other 6. And then the name, Whitney?
Sulfuric acid.
Good job. Okay, next one. Charge the cation. The iodine has to be the cation, right? And its charge actually has to be a +7. Because the oxygens are a -2, and then that would give us -8, and we need to have 1 left over. So we'll cancel 7 and the negatives out with 7 positives. And the name of this thing? Periodate. Okay. And the last one. Manganese with a +3 charge is our cation, and our anion is iodide with a negative charge. And so this is oops. Manganese 3 iodide, right? Transition metal. If a molecule is polar, what's occurring?
The electrons are being shared unevenly.
Okay. What types of molecules can be polar? And can't? Okay. All right, so we want to draw the Lewis structure, 3D model, and then a VSEPR 3D if it applies. So how do I draw the Lewis structure for this? What do I need to do first?
How many valence electrons you have?
So I've got 4 for the carbon, 3 for the hydrogens, and 7 for the fluorine. So how many is that?
15.
How many?
14.
Why am I putting the carbon in the middle? Nope.
You can build the most off of it.
It can form the most bonds. So that's what I'm going to put in the middle. All right, so the hydrogens are already happy with the 2 electrons that they're seeing. I have 6 leftover electrons, and if I dot up the fluorine, then the fluorine is satisfied with what's going on. Okay, so there's my Lewis structure. And what I have is 1 atom and 4 things around it, and all 4 of those things are what? Atoms. So then what's the structure?
Tetrahedral.
It's a tetrahedral. So I'll put a carbon here, I'll put a hydrogen there, I'll put a hydrogen there, I'll put a fluorine there, and I'll put a hydrogen there. Does it matter where I put the fluorine? Say no.
No, no.
Totally doesn't. It's like, here's my tetrahedral structure. Changing the position where I draw it is just like me doing this. Is it a different molecule? No. All right, so the nitrogen one. I've got 5 for the nitrogen, and I have 3 times 7, so 26 electrons. Are we okay with that? So why am I going to put nitrogen in the middle?
So we build the most off of it.
You can make 3 bonds, and the iodine can only make 1. Okay, and if I tack electrons around the iodines, they're going to be happy, and that'll leave me with 2 leftover electrons, and I'm going to put those on the top of nitrogen. So what is around, how many things are around the nitrogen?
4.
4 things are around the nitrogen. So that means I got a tetrahedral shape, so I'm going to draw so there's a tetrahedral shape. This is the Vesper drawing. And that's with the electrons. And then without the electrons, what does it look like? Trigonal pyramidal. If we hadn't drawn the Lewis structure and seen that there was a lone pair of electrons on the nitrogen, we would have assumed that this thing was planar. It was a triangle, but it would be flat. But it's not flat because there's a lone pair of electrons pushing those 3 iodines down. So that's why we need to come up with the Lewis structure. I can't just look at Ni3 and assume that since there's only 3 things that I'm in a trigonal planar shape, because there are a lone pair of electrons. Okay. Any questions?
Now, what did you say that
The one with the electrons is the
Fluoride.
Vesp. Oh, I'm sorry. Say again?
did you say it was polar? The CH3F, or did you mean something?
I didn't ask the question,
Oh.
but we can definitely ask the question. Is the fluoromethane, that first one there, the CH3F, is that thing polar or nonpolar? It's absolutely polar. What you have is no polarness between the hydrogens and the carbons. Everything's nonpolar there, but the fluorine is yanking hard. So this over here, this side over here would be negative. That is terrible. And this side of the molecule here would be positive. So that would definitely be polar, because I don't have anything canceling out the fluorine's pull. What about the nitrogen triiodide? It's polar. What you have is a pull of the nitrogen from the iodines, and so this top of the molecule is negative and the bottom of the molecule is positive. So both of those things would do what with water? They'd mix, for sure.